great honor to be here. And so one recurring theme in my research is Bond. Well, as you might have seen, so the talk that Terry gave yesterday, of course, like, we thought about a lot of that stuff in Binghamton, New York, but I think only the idea that that scissors congruence with respect to some kind of isometry group is homotopy orbits is like some kind of Farrow-Jones conjecture. The Farrow-Jones philosophy, I think, was definitely inspired by by Bond and our discussions with people in Bond back in the day. And the project that Julia talked about, of course, was started at the WIT that was hosted right here at the Hausdorff Institute. And now I have the honor to talk about a project that we literally started in 2016 at the trimester program, and which we have been working on ever since. And Kerry and I were again in Bonn in 2018 at Max Planck for a semester. We're Kerry for a year. So I will try to talk about the story starting at the CHEM in 2016 and where we are right now and some of the new things that we have been thinking about in the last years. Okay, so let me just start with some motivation for this project. Versus the very classical motivation that comes from wanting to classify manifolds is, so suppose that you have two smooth, compact, n-dimensional manifolds, and suppose that they are homotopy equivalent, then you can ask, is M actually diffeomorphic to N? Right, so this is diffeo. And one strategy to answer this question, right, it's a classical question, and a classical strategy is to first try to construct an H coordinate from M to N, right? So let me just give a reminder, right? So what does this mean? So a W, which is an n+1 dimensional manifold, with boundary given by M disjoint union N. So this is what makes it a cobordism, and then we want these inclusions of the boundary pieces to be homotopy equivalences. Okay, so suppose that you can, so I don't know if I should try to draw a picture. So there's not many very good pictures that I can draw of H coordinates, you see why. So if you can do this, then the next step would be you can ask, is your H coordinate actually trivial? And if yes, then you have succeeded, and this would imply that M is diffeomorphic to N. So the upshot of this is that we care about obstructions to H coordinates being trivial. Okay, so it turns out that these live in a group. So this is a big theorem. Well, I'm going to combine two big theorems, what's called the H coordinates theorem and the S coordinates theorem. So by Smale and independently by Barden, Mazur, and Stallings. Okay, so this is S coordinates, also called H coordinates theorem. So if the dimension of the manifold M is at least 5, then the theorem is that the isoclasses of H coordinates on M are in one-to-one correspondence with elements of the group, the Whitehead group of pi1 of M. And let me just remind you, so this is defined in terms of a K-theory group, so it's K1 of the group ring mod plus minus the elements in the group. And maybe I can say a little bit more here. So if you have an H cobordism on M. So the element that corresponds to it in the Whitehead group is called the Whitehead torsion. And so, right, part of the theorem is that the Whitehead torsion is equal to 0 as an element in this group if and only if W is trivial. So that's the obstruction to the H cobordism being trivial, the Whitehead torsion. Okay, so this was the classical pi naught level of, well, the pi naught level of the classical story. So now there is a whole space of H cobordisms. So let this be the space of H cobordisms on M, and then there is a stable version where you take the co-limit of the H coordinate spaces where you cross with intervals. And there is a famous theorem of Igusa that says that that gives the precise connectivity of this map. So this is roughly n over 3 connected, where n is the dimension of the manifold. Okay, and maybe the only thing that I want to say about this right now is that, so the reason why the space is very important is that, so this space, the stable H coordinate space, is one of the main ingredients in computing the homotopy groups of the diffeomorphous group, so homotopy groups of diff M. And there's some fantastic theorems of Hatcher, Weiss, and Williams that relate this stable H coordinate space to a space that fits in a fiber sequence with some other spaces that are accessible via surgery theory. And in good cases, you can combine all these things if you know the homotopy groups of this and the part that comes from surgery theory, that you can access this group. So, so this is why this is important in geometry. Okay, so now let me state also the classical theorem, which is the space level version. So the theorem of Waldhausen, but it was, so this was maybe first proposed in the 80s, early 80s, but only proved with all the details later in the 90s, together with Yaran and Rogness. Okay, so what this theorem says is that if we take the algebraic K-theory of a space X, this splits as, okay, so this is algebraic K-theory of X, which is the same with algebraic K-theory of the Waldhausen category Rx of retractive spaces over X. So this is a category with cofibrations and weak equivalences, and the purpose of why Waldhausen introduced this whole machinery was in order to define this algebraic K-theory of a space and to, well, at least propose this theorem and give a sketch of this proof, that this splits as a suspension spectrum of X times another factor. And this other factor, so when the space is a compact smooth manifold, this Whitehead spectrum is a delooping of the stable H coordinate space. Or what spectrum, or we can state it in terms of infinite loop spaces. So this is for M compact smooth manifold. So let me maybe make an analogy right now. Right, so the result that we saw over there, the result of Smale, Barden, Mazur, and Stallings. So one way to say it is that pi naught of this H coordinate space is the Whitehead group. Right, so this is defined in terms of a K-theory group. Well, I should have said the H coordinate space is defined in such a way that so the zero simplices are the H coordinates on M, and you have a path between them precisely when you have a diffeomorphism of H coordinates. So pi naught, by definition, is this set here, isoclasses of H coordinates on M. And I should have said also those are relative with inclusions. And so this was the pi naught version, and then Waldhausen's result is really a homotopical lift of this result. So this says that this entire space can be interpreted, right? So now interpreted this in terms of a K-theory space. Okay, so this is the classical story, like the pi naught level and the spectrum level lift of this statement. Okay, so now we want to start with the scenario where M is a smooth G manifold. So now my workout for the day.
You're not going to do the bad board work of just writing G everywhere and what you just wrote.
Oh, that would have been a very good idea, provided I erased the board. Yeah, so I should have maybe followed Kerry's idea and not erased the board, and then we could have looked at what I wrote and see where we can put the G's. Okay, but okay, so now suppose that M is a compact smooth G manifold. And there's still, of course, a definition.
G finite?
Yes. Well, maybe not for this definition, but for the rest of the talk, let's make it finite, because for many things it will need to be finite. So, great question. Okay, so an equivariant H coordinates on M. So it's what we had before, it's an H coordinates on M, but now it's also a G manifold, and it's such that these inclusions are G homotopy equivalences. So the homotopies, everything has to be G equivariant. And there is a lot of work dating back to the 70s and 80s on this.
Sorry, when you say G homotopy equivalence, you mean in the strict sense, right?
Yes, in the strict sense. So there's, and Wolfgang, please correct me because I'm sure I'm going to mess up some of the background. So I believe it might have been Illman who first defined the equivariant. So this is an equivariant Whitehead group. And an equivariant Whitehead torsion for an equivariant H coordinates. Is this correct with Illman first?
Geometrically, yes.
Okay, yes. So this was a geometric construction. So I'm asking Wolfgang because everything we have learned from Wolfgang's Habilitationsschrift. So, and sometimes it's, I know some results are due to you, and then some results were also the exposition of everything that was known at the time. So there was this geometric construction of an equivariant Whitehead torsion living in an equivariant Whitehead group. And okay, so maybe this was 70s. And then, so we will attribute this to you, Wolfgang, and maybe also Hauschild.
Yeah.
So the proof that this group splits, so this is now an isomorphism of groups, as the direct sum over conjugacy classes of the Whitehead groups of M, H, homotopy orbits with respect to the Weyl group. Okay, so now that the fixed point manifold, so it doesn't have a G action anymore, but this still has a residual action of the Weyl group, so this is the normalizer of H mod H. Okay, so yes, I think this is what I want to say about the pi naught level story. Well, I will say a little bit more.
So just inside, this doesn't seem to be a manifold anymore. So how is that? Why can't you find?
Yeah, so you can define it also for complexes, and well, we have also worried about this. So it turns out. Well, it turns out.
Okay. Okay.
So there's a lemma that well, I'm sure other people have thought about it. Kerry and I wrote it in one of our papers. It turns out that the fixed points for any, maybe I should write it as a side note here. So this, it doesn't have to be a manifold. Any fixed point space, that this is the co-limit of a representations of x times cross dv, where now I'm going to take the sub h. So these are points with isotropy exactly h. Okay, and now these are compact, and it's a WH equivalence. So you can just take a co-limit of compacts to make sense of that. But yes, great question. And I'm not sure, maybe Wolfgang was defining it directly on complexes and like in the book. But for sure we can do a trick like that where we can actually...
Sorry, I mean, I still don't understand what's going on here. I mean, the Whitehead, are you saying the Whitehead group depends on a manifold structure or not, or what?
Yes, I'm just saying this lemma doesn't depend. You don't need a manifold for this
But why
lemma.
would the Whitehead group depend on a manifold structure?
I think you can define Whitehead group for complexes too, right?
The problem is this, if you take H is not a defined CW complex anymore. You
But I
know?
mean, I don't know how the equivalent one is defined, but the non-equivalent one doesn't, right? Like, I don't know.
So if you have an arbitrary space, there's no finiteness. Nothing.
Yeah.
Yeah, the geometric things you have defined CW complex. If you go to algebra, there's no problem at all.
Okay.
Yeah, here you have a co-limit of finite complexes or something like that. Okay, so the theorem, the first theorem that we proved, so motivated by this result of Wolfgang, is the theorem. So we view this as the pi naught level version of the equivariant story. So the theorem that Kerry and I proved way back, so maybe it was published in 19, but this is literally work from the PIM 16 program, was to show that there exists a G spectrum, AGX, such that for a G space X, such that its fixed points split over conjugacy classes into the non-equivariant A-theory spectra of terms like this. So it's a Tom Beek-like splitting.
But you forgot to put yourself on the result.
Oh, thank you, Kerry. Yes, that's a bad omission.
And sorry, here G is a finite group.
Yes, here G is
compact
also-
G, for example.
Yes. So for the rest of the talk, G will be finite, because here, for example, G has to be finite.
Yeah, but it's not defined for a compact G, for example.
No, definitely not. So
we didn't define it for a compactly.
well,
Maybe someone else will.
it would be great. We just have no idea. So warning, or maybe first I should say that So since you asked about this, so it was very important to construct this as a spectral Mackey functor. And the technology for that only works for well, finite groups, maybe profinite, I can say something about, but yeah, I don't think anybody knows how to say anything about compact Lie groups. But that, of course, would be great. That's an amazing problem.
So I'm going to repeat the question from 2016. So is the H summand also the same as by taking XH cross EWH and then WH equivariant fixed points, like what would really appear in Topik's original formulation?
Yes, I think so. Yes, so the splitting, yes, so it goes in a bunch.
Okay.
And yeah, we can talk about it. I think we talked about this. And it goes into a bunch of stages, which is just like the Topik splitting, and then.
So in other words, it's also an element type isomorphism for this equivariant A theory.
Yeah, so I think you pointed this to us that you
but at that point, I think it wasn't clear.
But you can't take orbits on the outside though.
You cannot take orbits on the outside, so that's important. The orbits are on the inside.
No, on the outside you would have fixed points of WH, fixed points of XH cross EWH. That's what I'm just asking if this is analogous to the Topik splitting in that sense.
Okay, maybe let's compare the steps after.
Because
to
in
make.
the Topik splitting you would have
So for sure.
Homological groups of fixed points cross EWH.
So I think that is what you do. So, and then at some point, once you get free things like EW, like WH.
It's
you
kind of like
you
that.
can pass through the homotopy orbits on the inside.
You kind of have to mimic those things, but do it inside in the categories instead of outside on the spectrum.
Okay, we can compare the steps again afterwards. But by the way, this was written so we're using part of what's written also in this paper by Badzic and Dorabiala. And I think the splitting was known to Rogness, not that there is a G spectrum, which is what we were trying to achieve, but just, well, maybe I can tell you quickly. The category that achieves this is the category of retractive H spaces with genuine H equivalences. And that one at the category level you can show has the splitting, but at some point there is the additivity theorem that you have to apply, so it's really a splitting only on the spectrum level. And I think it goes exactly in the you treat WH things, and once you have free things, then you can identify with the homotopy orbits on the inside. Okay, but the wording here is that, so this is not the K theory or equivariant K theory of the category Rx with G action. So it's not just K theory with G actions. So if you consider what you get by taking the equivariant K theory of this category with G action, that gives rise to another theory that Kerry and I also worked out in Bonn. That we called AG course, whose fixed points are bivariant A theory of a vibration. So it's not this. So for this, so this is a little more subtle. So you can take the homotopy fixed points of these categories, but then you really want to refine the weak equivalences in each one of these to be the actual genuine equivalences for every H.
But these fixed points are the K theory of retracted G spaces over X, right?
Yes, but what's important, so for both of them, those are the objects in both theories, AG course and this. But weak equivalences for that are the coarse ones. Weak equivalences in every fixed point category here are the genuine ones. So yes.
And sorry, another question: does this commute with restriction? Like if you have a subgroup H of G, does the restriction is just HX?
So
I
yeah.
think so.
Yes, I mean we have the restriction and transfer maps. And
Sure.
And then there's an interesting question about what, so we have explicit restriction and transfer maps at the category level, and then there's an interesting question about what they do like on the splitting. And so two of my PhD students, Maxime Tage and Andres Mejia, are working that out. They said that they did work out formulas for it, but so maybe you'll see that in the future coming up from young people. So I think this is Okay, so we want to move into the future. So we can discuss this again. I think we have discussed this at length in the past also. So I'm not going to say more now about this construction, but yeah, so the main property of this construction that we wanted at that point was the splitting on fixed points. And it is clear why, right? Because the pi naught we know that we want, or pi 1 that we want to achieve, there's this kind of splitting. Okay, so let me make the conjecture that we want to make about this, which you can expect. So the conjecture is that the spectrum actually splits as a suspension G spectrum times another factor with the property that when X is a compact smooth G manifold, then on G fixed points, well, let me maybe write out. So if I take this and I take the G fixed points, I get, of course this is not defined yet, right, but I get a space of a stable space of equivariant H coordinates. Okay, so towards this conjecture, so a theorem that we proved more recently, so probably we worked on this, maybe it was published now, but I think we worked on this a lot in Bonn in 2018. There exists a map from the suspension G spectrum of X to AGX. Okay, so we constructed such a map that has the property such that for X being, okay, all these adjectives, a compact smooth G manifold on G fixed points, the fiber is also has such a splitting. So it has a splitting over conjugacy classes into the stable H coordinate spaces of MHW, well, homotopy orbits of this. And so again, before Thomas asked, so the way we define this, we just define this gadget to be the colimit of the H coordinate spaces of those things that are actually compact manifolds by the result, by the little lemma that I pointed out before. So we can just define it like that. Well, that's what we do, that's what we show explicitly. Okay, so what do we want to show now to move closer to this, right? So here we never really, well, like this thing doesn't a priori exist. So what we want to show from this point on, okay, is two things. So number one is we want to show that there exists a stable equivariant.
All I can ask is because we put 22 there, but isn't that this? I was reading the paper, listening. Sorry, but isn't that the paper from 2020? Or like I'm confused. Isn't that the result that's in the non-manifold copy?
Sorry, so there's, okay,
It's
so
the
that paper,
non-manifold.
I put the year when it was actually published. So this paper, I think, was published in 19, but this is the same. So this, I think, we worked on in 2000,
Yeah,
like,
sorry.
when we were at the HIM in 2018 and so on, but I think, you can correct me if it's wrong, I think it appeared this last year, but maybe 21, anyway. So it's a different paper, more recent, but also work done at the, we're not cheating at all, it's all the work done in Bonn, in this, well, except from here on where maybe, even though I think we started talking to Tom Goodwillie while we were at the HIM in 2018, the first time we had a Skype call, I remember, from the Max Planck Institute to Tom Goodwillie, and that was the first time I think we talked to him on Skype.
What was in 2018 in him?
No, not
No,
at
we were
HIM,
Max
we were
Planck.
at Max Planck,
Yeah.
remember? You were not there, yeah, you missed out the whole semester of fun. Okay, so we want to show the following two things. So there exists a stable, equivariant H cobordism functor from compact, smooth G manifolds and smooth equivariant embeddings to spaces which would send M to some kind of stable H coordinate space, equivariant H coordinate space. So we want this to be a space of, well, stable space of equivariant H coordinates. Okay, so first, what does stable mean here? So what does the infinity mean here? And for this, let me illustrate what we need for this with also an old theorem that we also learned from Wolfgang's book, even though this is really funny. Well, we read this paper by Araki and Kawakubo, but in Wolfgang's book, this is an exercise. And then since you practice look out, and it's a whole paper. So you can do this as an exercise in the talk if you'd like her to prove this theorem. It is an exercise in Wolfgang's book. So it's a whole paper by Araki and Kawakubo. So what it says is that if you have an equivariant H cobordism between M and N, then this equivariant Whitehead torsion inside the equivariant Whitehead group is equal to 0. Okay, so remember the non-equivariant story, right? Whitehead torsion was 0 exactly when your H cobordism was trivial. So this was the obstruction to the H cobordism being trivial. So equivariantly, so even on the pi naught level, this is not quite the case anymore. But what is true is that this is 0 if and only if there exists a representation W such that when you cross with the representation disk, then it becomes, so I see that some people cannot see, this is better. So there exists a representation such that W crossed with dV, so this is the representation disk in V, that this is trivial. So this is M times dV times I. And I always has the trivial G action.
Now remember the exercise. The point is, without this, is so we have a weak gap hypothesis. Right? And
So-
the question is, we only make sure that you have this gap hypothesis, never is really in the exercise. So
For the exercise. So if I am going to have time at the end, which probably I will never get there to talk about like the part 2, like I was going to go into the isovariant stuff and the weak gap hypothesis. But yes, the exercise is not so unreasonable. Like there's enough in Wolfgang's book, enough theorems that you can get this exercise. Okay, so
do they really use Illmann's construction or they?
yeah, so this is the Whitehead group. Illmann's construction. So
they
we're
do this
talking about this classical,
triangulation kind of things.
yeah, this geometrically constructed Whitehead torsion. Okay, so now I'm going to define this equivariant H coordinate space. So the stability part, at least, we know we want this to be a colimit over representations of H M times dV. Okay, so. Okay, so Okay, so we have this. So this is one thing that we want. We want such a functor, and then part two is we want to have a splitting of this H-coordinate space over conjugacy classes into non-equivariant H-coordinate spaces of such factors. Okay, so these 1 plus 2 are joined with good Willy and Degussa. Okay, so maybe I should say that when we started this project way back, Kay and I think we did not know that 1 was even going to be an issue. I think we assumed that that's given, and it follows from things in the literature. And then that the whole project would wrap around, much faster, that we can assume nice properties and functoriality of an H-coordinate functor. Okay, so it turns out we're wrong. And
Can you say a few words about what the issues are?
yes, so now let me talk a little bit about part 1. Yes, so functoriality is very subtle. And so there is a long story here in Bonn also, which is, so maybe some of you are aware of Malte Pieper's thesis, which was also trying to address this problem. Okay, so I think in 2018, right before we went back to the US, we talked to Wolfgang, and Wolfgang encouraged us, well, he told us about Malte's thesis. So Malte was a student of Wolfgang, who was also given this problem to work out the functoriality of the H-coordinates or pseudo-isotopy functor, so even non-equivariantly. So Wolfgang said that he was sure that this was not written carefully anywhere, so we could not find it anywhere. We've been going through the literature, So okay, one first issue that people really hand wave about, which doesn't seem to be made precise anywhere, is this thing about rounding of corners. So everybody would say up to rounding of corners, which if you think about it, when you start doing the stabilization procedure and so on, there's an unwieldy coherence problem that just seems, okay, so both Malte and us are working with manifolds with corners, because and I should say the Waldhausen, Jahn, and Rognes result is very precise, of course, but they work with PL manifolds. And then there's some theorem of Hatcher or somebody that shows that if you have that result for PL, then it implies it for the smooth case, but they never really work with the smooth functor, with the functor for smooth manifolds. Okay, so, right, so
sorry, Mona, may I ask one question? So, if I understand correctly, you're first making it a functor, and then you're proving as a functor it's equivalent to another functor, right?
We're using infinity categories. so this is the craziest paper that has infinity categories and analysis.
I mean, how is this better than just saying there's pointwise equivalence and we use that to make it a functor?
Wait, what do you mean pointwise equivalence?
Let me just make it separately.
You mean if we don't have compatibility, if M is included in some others?
Just confused, if you don't have 1, can you use 2 to sort of make?
Oh, no, yeah, you're right. You could do 2 separately. No.
we
somehow the fact that
So, yes, it's better. Okay. You could do 2 without 1.
Yes, and then you can deduce 1 from 2.
No, we can't do 2 without 1.
Okay, no, you're using 1 and 2, but I think you could. Okay, you wouldn't have a functor,
To
but
get
you
the
could
splittings
put
to
this.
agree with the stabilization, we use functoriality.
But I think you could do things in the homotopy category, maybe.
Yeah.
Okay, anyway, it is plausible that you can do 2. So you can always have something to the homotopy category. So it's possible that you can do this one at a time. So it's very good to have the result 1, because then we can use it a lot for this in the construction of the splitting. But I think no, at some point
I don't think we can do 2 without 1.
well, at some point we were considering writing paper 2 without.
What would you write on the paper? Yes, what you want to
We're
say.
gonna black box it.
Yeah. So
Yeah.
no, but you could backrock something to the homotopy category. Well, anyway.
Okay, so I want to have an idea of how the H-coordinate space is a functor, not that there is some functor that
Okay, we can debate later. So
I mean, one is a nice thing.
Oh, of course, yes. Yes, so we really want one, and if we want, right, all the, like, we want everything to fit into a covariant parameterized H cobordance theorem, we definitely want, you know, the nice functoriality property, and it is very useful. It makes this a lot easier because now some of the maps you can use functoriality. But I think you could try to approach that by just thinking that you have a functor to the homotopy category and just try to show the splitting.
So if I understand correctly, the issue with one is not the definition of like HG, but the stabilization, to show that the stabilization procedure is functorial, right?
Yes, so let me show some things that some of the ideas that go into here. So yeah, as I said, like we are constructing it as an infinity one functor, so I will get to this at the end, but even that, right, you need to you need to build a coherence and show that, well, you have what you need in order to construct that. So what Malte did, so of course, first we also thought it would be very good if Malte had not quit math after his PhD thesis and he would have tried to publish his thesis. So his thesis is extremely impressive, very long and very, very complicated. And well, we knew it's never going to see the light of day because he quit right after his PhD, and I think we talked to him once, and then he, I think we're never able to contact him again. He disappeared. And but it's also it's extremely complicated. So Malte also works with manifolds with corners. So he also constructs this as a map of quasi-categories. So he does some crazy thing of like building the map on the lower simplicial levels and then using some obstruction theory to construct it on the higher simplices. There's some very complicated stuff in there with Eubanks that I will talk about it in a minute. So anyway, our idea and encouragement by Wolfgang was to try to do this in a simpler way, to see if we can just do this, because we knew that we cannot quote Malte's thesis because it will not be published, and it also looked very complicated. It's not like we could just read it. And so we figured, okay, let's just start from scratch, inspired by his work.
We're also making it equivariant.
Yeah, and we also need to make it equivariant. And he did it for pseudoisotopies, and we need to do it for H cobordance, which it turns out it's a little more complicated and subtle at some point. So we're actually doing it for H cobordance and not for pseudoisotopies. But now I'm going to cheat and talk about pseudoisotopies because in a talk it's easier to talk about pseudoisotopies. So let me just show some of these ideas. Okay, so now think about pseudoisotopies. And so these are diffeomorphisms of m times I, which are identity on m times 0, and if m has boundary, then also union boundary of m times I. Okay, so now let's just think about what would be a stabilization map from taking a pseudoisotopy on m, and if you wanted to create a pseudoisotopy on m times I. So this is still very classical stuff that shows up already in Igusa's paper, well, defined by Hatcher, and that shows up in Igusa's stability paper. Okay, so we have an F like this, and we would like to create a pseudoisotopy like this. Okay, so first of all, you can't just cross with I because it would not be identity on the relevant part. So the first idea that, okay, so all of these ideas, we will call them the Igusa black magic box. So idea one that I think Igusa had was, so let's just think, so this is now like the square I times I. So imagine this, so we need to cross this with M. So imagine this where we draw these rays and we define this by applying F to each line segment and then identity outside. Okay, so this at least is going to satisfy this. Okay, so we apply F, so this is M, each one of these is a copy of M times I when I cross with M. So I can apply F to each one of these rays and just make this identity outside. So each point on this square is a copy of M. Okay, so this is a great idea, but the problem is that we need to put a condition to make this smooth at this cone point. So a condition to make this smooth at the cone point. Okay, so the condition is you just start not with all the pseudoisotopies, but you can require them to be a product near the top. And it turns out you can show that the space with pseudoisotopies with that condition is equivalent to this space, so that's fine. Okay, but then there's still a further problem. Okay, so this works, you can define the stabilization and it's smooth, but then the problem is that stabilization loses this condition. So the stabilized pseudoisotopy is not going to be straight at the top anymore. Okay, so the next idea, well, in the meanwhile you can try to come up with the next idea yourself. That's an exercise while I raise the board. Okay, so idea 2, and this is what Igusa used in his stability paper, is to use U-shapes instead. Okay, so again I will draw the square like I times I, and we want to cross everything with M. So instead I'm just going to draw a U-shape like this. So now we want to define F. So again, it's going to be F on each one of these line segments, identity outside, and here we want to make it the diffeo, well, the thing that's diffeomorphism on n times 1 given by the pseudoisotopy. Okay, so this is good. So this works. Now you can compose 2 of these. So this is precise enough for that, and this is what Igusa does in his stability paper. So this is the stabilization that he uses, right, to compose. So now you can compose this with another one, and okay, but of course in that paper he never considers like how do we compare this if we were doing it all at once, right? So this is still not, you still don't have functoriality, but at least you can precisely define this co-limit and will prove his stability result. Okay, so now the best idea yet, also Igusa black magic. So, okay, I see I only have 2 minutes, so maybe let me see how I make this.
You can take another 2 more minutes because you were interrupted too often. So.
Okay, so yeah, so this last idea. Okay, so if F is a pseudoisotopy, we can define the double. So this is a definition. The double of F is a map from M times minus 1, 1 to minus 1, 1. So really just double F. So this is a map that's F on minus 1, 0 and commutes with the reflection.
So it's doubling across the top of F?
Yes, so it's doubling, right? So, well, we have M times I, and now we have another copy, and it's the thing that doubles F. And now we can also make a definition. We can say F is, so this is our terminology. You can tell us if you don't like it, since the paper is not out yet. We call F mirror if the double is smooth. Okay, so claim 1, maybe I won't write this down, is if you restrict to mirror pseudoisotopies, you still get an equivalent space. So instead we will work with mirror pseudoisotopies. And now this is really like magic. If you have a mirror, so for an F that goes from, M times, okay, I can define the stabilization. Okay, so now I want something that goes from m times the disk times, so I want to define another mirror pseudoisotopy, but on m times dV. Okay, so let's pretend dV is an interval so I can draw it. So if we draw the picture, so now this is your -1, 1, and this is your dV direction, and everything is crossed with m. So now the mirror thing, the f bar, lives on it. Like I can put each one on one of these diameters. So I apply f to each one of these and identity outside the rest. Okay, so it turns out that now you can write a formula for this, and it's very nice and easy. And the miracle is that now this is smooth, and this is still mirrored. It's also equivariant if you have something equivariant. And well, and the smoothness here uses some, well, so here's where a little bit of analysis, magical analysis comes in, that the components you can see of this function are an even, or you can make sense of even and odd as a function from m times any symmetric interval. And then there's like some little magic stuff that lets us prove smoothness. So maybe we can tell you about this after the talk. And mirror. Okay, so as I said, this is much easier to explain for pseudoisotopy, so that's why I did it. But now the claim is you can take this idea and make it work for H-cobordisms also. So for H-cobordisms, it's going to be the same picture where you put the H-cobordism along the race. But also another really magical thing here. If you do this twice, this is actually equal. Sorry, not isomorphic. This is actually equal to this. Right? Insane. But if you do it for H-cobordisms, you do have to work a little to prove smoothness at this comb point when you define your stabilized mirror H-cobordism like this. And this is not going to be equality anymore, but you can define a nice isomorphism there. And then using these isomorphisms, okay, so I don't have time to write anything down, but I will just say in words the last important idea also, which I will credit Keres with, that we really needed in this paper also, is when we compose, so for functoriality we also need to compose, well, we have embeddings and we want to compose embeddings, but if we work just with vector bundles, well, two disk bundles do not compose nicely to a disk bundle because the structure groups don't work out, so you can also have to relax for the embeddings that you work with, you have to relax the structure groups to not be ON anymore, or OV anymore, but be something that we call round diffeomorphism groups, which are just diffeomorphisms of the disk that preserve the spherical shells. Okay, and then with that, if we use round bundles as opposed to vector bundles, we can actually get strict associativity wherever we want using these isomorphisms, and we can construct. So I also should give Nima credit because he taught us the correct. So we've been struggling with infinity category, like which framework is the best, and we're trying to do this also with quasi categories for a while, but it was pretty complicated. But then he taught us exactly which results from Siegel spaces we need. So what we literally do is construct a left vibration of Siegel spaces over the simplicity enriched category, so category equivalent to smooth equivariant manifolds and embeddings, and then by the black box we get the functor that we want. So there's lots of ideas that I really hand-waved in the last few minutes that we can talk about more. But well, I think these are some of the pictures that I think you can see throughout the history of the literature that make this more and more precise. And hopefully we will finally have like a precise story once we finish this. We still need to figure out one last bit of analysis. If anybody knows about Crochet?
We don't have to solve that.
Yeah. So maybe, yeah, I will stop here and then